So we now want to study the exact same thing, except in the quantum theory. In particular, we want to derive the quantum version of Noether's theorem. We'll see this leads us to a concept of something called the ward identity. Okay? So in particular, we're going to study this in the path integral. In other words, we're going to study the following functional integral, d phi a times the exponential of is phi a. Now, just like before, we're going to do the symmetry transformation. Phi a goes to phi a prime, which is equal to phi a of x plus epsilon of x delta phi a of x, where again I am doing the variation by a space-time dependent symmetry parameter, just like in the previous video. And I now want you to consider this as a change of variables in the path integral. Okay. So the first thing to note is that, like any change of variables, this does not alter the numerical value of the functional integral. So in particular, if I had integral d phi a exponential of is phi a, this is obviously the same as the integral d phi a prime exponential is phi a prime, independent of the relationship between phi a and phi a prime. So this is true for any change of variables, whether it's a symmetry operation or not. This is always true. However, because it's a symmetry operation, we can do a little bit more. In particular, you can convince yourself by discretizing the measure. So this is a bit formal, but you can imagine breaking the path integral measure up into many little things at different points in space. And then imagine doing a little integral at each point in space, as we did at the very beginning of this series. You can convince yourself that under the symmetry, the integral d phi a, the integral measure, is the same. Okay? The measure does not transform. This is usually true. In fact, there's a sort of very beautiful series of exceptions to this rule. Whenever this rule is not satisfied, you get something called an anomaly. And this is a really surprisingly beautiful exception, which tells you a lot about sort of symmetries and how they're realized in quantum physics. We're going to assume that this is not happening and that this is actually equal. Okay? You can learn more about this in more advanced classes. We're going to assume there is no anomaly in this, which means that the path integral measure does not transform under the symmetry. We'll take this as an assumption. And if you can discretize your measure in a simple way, then this is actually true. Okay. However, the action does change under this transformation. So let's think about how it changes. We saw last time that to first order an epsilon, s of phi a prime is equal to s of phi a minus the integral d4x d mu j mu times epsilon. Okay. So if I now take these two things, this fact that the measure does not transform and that the action does transform in a simple calculable manner, and I plug these two things into here, then what I find is that I can write an expression of the following form. On the left-hand side, I have the original thing, which is integral d phi a prime times the exponential of is phi a prime. And on the right-hand side, I have now, replacing d phi a prime with d phi a, and expanding out the exponent, I see this something like this. d4x, d mu j mu times epsilon of x. And this is all true to order epsilon square, and it's all multiplying the exponential of is phi a, the original phi a. And excuse me, sorry, this was never, okay. So this is now what I have for the right-hand side of that formula. And we recall that this whole thing was, of course, equal to the integral of the thing without any primes ever. So this whole thing is equal to integral d phi a times the exponential of is phi a. Okay. Now what's happening here? Well, this one bit I can cancel across this whole thing. And this path integral that I'm computing, the path integral of d mu j mu with the same usual measure, is exactly what you do if you're interested in computing the expectation value of d mu j mu. So this path integral computes the time-ordered expectation value of d mu j mu. I guess there's no need to put a time order in here because there's only one operator here. But this computes exactly d mu j mu from the path integral. And so because this must hold for any epsilon, we conclude that d mu j mu of x is equal to 0. The expectation value. Okay. So, this is a nice result. It kind of makes sense. We did some path integral stuff, and this, in a sense, is part of the quantum version of Noether's theorem. Now, if you look at this, though, so let me just write that down. This is part of the quantum Noether's theorem. So we've concluded that the expectation value of d mu j mu in the vacuum is 0. If you look at this, you might be tempted to conclude that d mu j mu is 0 as an operator. In other words, it's 0 in all states, not just the vacuum. That turns out to not be quite true. So to understand that, let's now look at a slightly more sophisticated problem. Let's apply this, the same logic, not to the generating function itself, but to the following expectation value. To the expectation value of the following time-ordered correlation function, phi b of x1, phi c of x2 in the vacuum. Now, by the usual path integralology, this is 1 over z0 times the integral d phi a of phi b of x1, running out of space here, times phi c of x2 times the exponential is of phi, all the phi's. Okay? Now, by the arguments above, this is also numerically equal to the following path integral, 1 over z0 integral d phi a prime, phi b prime, x1, phi c prime of x2, with the exponential of is of phi prime. This equality follows just from changing variables in the path integral. It's not even really changing, it's just relabeling. It's calling phi prime. Okay, but now what we do is we now connect all primed quantities to unprimed ones by using the symmetry transformation. Remember, the symmetry transformation was this thing right here. We now use this to connect all unprimed variables to all prime variables. Okay, so what do we find? We find that this expression here becomes, here we go, this is a bit lengthy, the measure does not change, phi b prime becomes phi b of x1 plus epsilon delta phi b of x1. Phi c prime becomes phi c of x1 plus epsilon delta phi c of x2, sorry. And finally, this term here in the action transforms the way that we worked out last time, a few minutes ago. Transforms like d mu j mu of x, epsilon of x. And the whole thing is correct to order epsilon square. And the whole thing is now multiplied by s on the unprimed action. So phi a, unprimed. Okay. Okay. And now, of course, you understand the drill. We set this equal to its unprimed version. Because remember, this whole thing is equal to this, which is the path integral with everything unprimed. So set equal to the unprimed version. And really what is happening is that the things without epsilons will cancel, which means that if this is equal to the unprimed thing, everything multiplying an epsilon must vanish. And those terms, let me just group them all together, take the form epsilon of x1 delta phi a x1, delta phi b of x1 phi c of x2 plus epsilon of x2 phi b of x1 delta phi c of x2 minus I phi b of x1 phi c of x2 times the integral d4x epsilon of x d mu j mu of x. Okay? And this whole thing is equal to 0, but when I say equal to 0, I mean that everything is, of course, path integrated with this measure. So everything is in the path integral. I'm not writing that down, but the whole thing is in the path integral. So what that really means is we're computing the VEV, the vacuum expectation value of all of these quantities, and it's equal to 0, which means that we've actually shown that the following relation holds. So this is just coming from this part here. And this is equal to delta function x minus x2 plus phi b of x1 delta phi c of x2 delta function. And excuse me, there was a typo in the above line. This was x minus x1. Okay. So this implies this. Okay. And formally speaking, this is true because this line holds for every epsilon. Because of that, we require this relationship to be true. If you're confused about where these delta functions came from, what you should do is integrate this expression against some test function epsilon, and you'll see that you will recover this structure. Okay? So in particular, there's an epsilon of x1 here and a delta phi b of x1. That's why over here there's a delta function here with x1 when it's the phi b at x1 which is transforming. And if these words that I'm saying don't quite make sense, just pause the video and take a second to integrate this expression here against the test function. Okay, now what does this mean? The point is that d mu j mu is not actually 0, okay? Because we just computed a correlation function of d mu j mu with other stuff present, and we got a non-zero answer. So the real way to think about this is that j mu isn't quite conserved. It's conserved up to these delta function terms where other operators are inserted into your path integral. Okay? So if we look at correlation functions of j mu, or rather d mu j mu, with operators that are charged under the symmetry generated by j mu, then j mu is conserved up to delta functions where those other operators are. Okay? And those delta functions appear at the location of the insertions of the other operator. Okay. So this idea that the current isn't quite conserved, but it is almost conserved up to these delta functions is called the Ward identity. This is the Ward identity associated with j mu. Okay? Or rather associated with the symmetry. Okay, so now you know what a Ward identity is. It is the almost conservation of a current in the quantum theory. And just a few more words. These delta functions are sometimes called contact terms because they appear only when 2 points are coincident. So for example, the insertion of the current operator at x must be at the same point as the other operator phi for this delta function to contribute to anything. Okay. So that concludes our discussion of the Ward identity. I want to point out this was all quite abstract, so it might be illuminating. I encourage everyone to work out the details in the U1 example that I discussed earlier. So in the U1 example of a complex scalar field. This is an interesting thing to do. Okay, so that concludes our brief discussion of symmetries in the functional formalism. Next, we're going to move on to fermions.